let's see. The students who come in person will get hard copy handouts, but all this material is on Brightspace, and I'll just show you what it looks like, so you'll know, when you're getting the right one. This is today's lecture is on chemical composition. Looks like that. And I also have a review document that's in that same module with this exam 3 material. And it looks like that. In fact, it looks exactly like a paper exam. And that's on purpose. So that if you're so inclined, you can treat this as an exam. And then there's also a key in Brightspace, and you can check your answers and see where you're weak and work on your weak spots. If you can't figure out the answer to a problem that you missed in the review document, then the next place to go is this worked problems. And this document shows you how I worked each one of those problems. If that's still for you, then bring the problems with you and come see me, or Zoom in when I'm in office hours, and we'll iron out those specific problems. Let me see it. Mark just zoomed in. Okay. So, and at any time during this discussion, you can interrupt me if something's not making sense, or if something clicks and you have a question, you can stop me. Otherwise, we'll move on. Let's see, let's put that up there somewhere. About there. Okay. Material for for exam 3, chapter 8. And this is the topic, chemical composition. What we're going to discuss in this chapter, in this material, has to do with how do we know, or how can we quantify what's happening on the microscopic level when we can't see it. Right? There are certain measurements we can make, mass, volume, temperature, other types of measurements we can make macroscopically. But on the microscopic level, that's where the action really happens. So we need to make a connection between what we can see and what we can measure and what we can't see. And that's what we're going to try to discuss and bring into focus today. All right. I'm not going to stop here for very long, just to say that the first topic is counting by weighing. So we'll go straight to counting by weighing. What we've learned over the centuries in chemistry is that when a reaction takes place, when you bring two or more substances together and they interact in a chemical fashion, they're not doing it based upon their masses. They're doing it based upon the identity of each of the atoms, the molecules, and the numbers of the atoms and molecules. So it's a numbers game. It's not a mass game. So that's our first hurdle. We've got to figure out how to count atoms and molecules with something that we can measure. And that's where we're going to talk about counting by weighing. In order to use this method, each of the objects, each of the atoms don't have to have identical masses. They can vary. What we need is a handle on the average mass of an atom. If we have an average mass, then we can weigh them. We can get a mass for the total and use our dimensional analysis that we've learned so far, conversion factors. To get it from the mass, we can change it into numbers of atoms or numbers of molecules. So the key here is to figure a way to determine the average mass of an atom, of an element. All right, so that's where we're headed. And the example, let's see, I think we've got an example here coming up. Yeah, here's the example. Suppose we have a jar of jelly beans. And the question is, how much does 1,000 jelly beans weigh? That's our starting point. They don't all have to be the same mass. Right? And we don't have to weigh all 1,000 of them. I mean, it could have been a million, could have been a billion jelly beans. What we want to know is what's the average mass of the jelly bean. So we could just take a subsample, say, in this case, 10 jelly beans, and put them on a balance, right? And in this case, what we've done is we've taken individual jelly beans. That's one way to do it, to get an average mass. Or you can weigh all 10 of them and just divide by 10. But we'll stick with this for now. Each jelly bean has its individual mass, right? And we've measured them here. All 10 of them have different masses. What we want is an average mass for a jelly bean. And it's simple mathematics. Just add up the total and divide by the number of jelly beans, and you get an average mass of 5 grams for each jelly bean. So to clarify, this value is 5 grams per jelly bean. That's the average mass of our jelly bean. Now we can use that information to find out, to calculate the mass of 1,000 jelly beans. So if we start off with 1,000 jelly beans, I'm going to abbreviate there, jelly beans. Then we can use this as a conversion factor. Right? Excuse me, that's not right. This is in the numerator. So our conversion factor has to have the jelly beans in the denominator and the grams on top. Right? And so this is for 1 jelly bean. Notice with this conversion factor, what we can do is cancel the jelly beans and convert it into mass. So that's 5,000 grams is the total mass that we calculated for 1,000 jelly beans, and we didn't have to weigh the whole 1,000 jelly beans. We just needed to know an average mass for each jelly bean. Now think of jelly beans as atoms. Right? If we wanted to know the mass of 1,000 atoms, we needed to figure out what is the mass of the average mass of an atom. And then we could tell you how much that many atoms would weigh. So that's the trick, trying to figure out what's the average mass of the atom for an element. Okay. Okay, so let's see. Here we're comparing different objects. We have 2 different samples containing different types of things. We just call them one's A and one's B. So you can think of this in terms of atoms too. We've got a sample with A types of atoms. And if it helps, you can just pick one of the elements, right? You could have A would be zinc and B would be copper. There would be different atoms. And if we say that they both contain the same number of atoms, exactly the same number, then if we weigh the two, they should not have the same mass. Say we have, let's go with our example. Let's say we have zinc atoms here, we have copper atoms here, and say we have, let's make it big. Let's say we have 1 billion atoms of zinc. Okay, 1 billion. That's a big number, but it's just a number. We've learned how to write big numbers, right? Correct. Suppose we have the same number of copper atoms. So this is all hypothetical, right? We didn't actually count out 1 billion atoms. We're saying that suppose we could do that. We had exactly the same number of atoms of each, right? And we put those atoms on a balance and we discover the mass. So this has a certain mass of zinc atoms, and this one has a certain mass of copper atoms. Right? They're two different values. Because we know that atoms don't weigh the same. If they're different elements, they have different masses. Right? We learned that from our periodic table when we studied that. You go along and you see different values, right? You see atomic numbers are different, and atomic weights or atomic masses are different for each one. So we know that they're different masses, right? So we should expect to get a different mass here than here with the same number of atoms of each. Well, if we ratio these two, if we say the mass of zinc is ratio to the mass of copper, okay, we just put that ratio together, and we know that they're exactly the same number of atoms, then the ratio of the totals is the same as the ratio of the atoms. So this should be, let me call this total mass. Total mass. There we go. So the total mass of them, now we ratio them. Well, the atomic mass of zinc and the atomic mass of copper, the ratio is going to be exactly the same because we have exactly the same number of atoms. Okay. We could have, I don't know, 100 billion of each one. It would be a different value here, but the ratio would be the same. Atom to atom is the same as total to total because they're exactly the same number. So that's our target. We want to know if we're going to get a handle on individual atomic masses, we need to know how to ratio them. Like this. We need to know how to say our samples are exactly the same. That's our target. We need to figure out how to determine exactly the same number of atoms of each of the elements. Then when we ratio something that we can measure, we can infer ratios of individual atoms. This looks like we're going backwards. We've got a pile of marbles that weighs 394.8 grams, and we pull out 10 of them, and we weigh them. Okay, so we can infer from this information how many marbles we have. And here's how we do it. This is again dimensional analysis, conversion factors. So if we have a pile of marbles that weighs this much, the total mass is equal to 394.80 grams. Well, we pull out a subsample, 10 marbles, and we say that 10 marbles, 37.6 grams per 10 marbles. Right? So each marble weighs 3.760 grams per marble. Right? That's like 10 atoms that we weigh them. And we find out that each atom is that mass. Now, no atom is going to be that big, but it's sort of analogous to doing it that way. So now we have a conversion factor, right? Remember, conversion factors are usually ratios. So we can take this value and use our conversion factor. We need grams on the bottom and marbles on the top. Now, first of all, will that give us the answer we want? Is that going to give us numbers of marbles? How many marbles? Yeah, right. Because marbles is here, grams cancel. Well, we have to put that value in there, 3.760 grams per marble. Okay, so 3.760 into 394.8 should be here. So that equals 105 marbles. What we need to know is, what's the average mass of a marble? So we can think about that in terms of atoms. What's the average mass of an atom? Right, so many grams per atom. Then if we weigh a sample of atoms, we can use that value to tell us how many atoms we have. Now we know that atoms are very small, so their masses are going to be extremely small also. We learned how to express small masses in scientific notation, right? But that's not always convenient either. So scientists came up with another unit. They call it the atomic mass unit. Sometimes you'll see it just this, like that. I prefer AMU. Right? It's not confused with anything else, where you can get lost in the sentence. AMU is unique and less likely to be confused with anything else. Right? So this atomic mass unit has been determined to be that value. Now, how we did it is very complicated, but it has been done. This atomic mass unit is that value, and I hope to give you some insight in a few minutes how we arrived at that value. But if we know that this atomic mass unit is equal to that mass, then remember, if you have an equivalence, you can also generate a conversion factor. Right? We did that early on in the semester. It would be 1 atomic mass unit per 1.66 times 10 to the minus 24 grams. Or remember, all conversion factors are equal to 1, so you can flip it if you need to. You could say 1.66 times 10 to the minus 24 grams per 1 atomic mass unit. Either way, depending on what you're starting with. If you're starting with a mass, which is usually where we are, a mass of atoms, and you can measure that, then you can use this conversion factor to say, all right, how many atomic mass units is that? Okay. Now, when we say 1 atomic mass unit or 12 atomic mass units or 50 atomic mass units, per atom, we're still speaking in averages, right? Because we know that every atom of an element is not identical. We've studied isotopes. Isotopes have different numbers of neutrons, which changes their mass. But it's still the same element. Why? Because they still always have the same number of protons. That's why they're the same element. But with different neutrons, they have different masses. So what we're saying is that when we have an atomic mass for an element in terms of atomic mass units, that's an average value. All right. So now that we have these units that we can use for small things like atoms, we need a standard. Right? We've got to fix a point. Otherwise, our measurement unit just kind of drifts all over the place. We have to set it in concrete. We have to set it and fix it by some standard that everybody agrees upon. And from there, we work our way out. And that standard happens to be carbon. And it used to be, years ago, when scientists were first settling upon some standard, they tried oxygen first. And the reason they did that was because most elements in the Earth's crust, most elements on the Earth, in fact, are some combination with oxygen. All the metals in the Earth's crust, except for maybe gold and platinum and palladium, will be combined. Not always, but many of them are combined with oxygen. So they thought, well, maybe oxygen was a better idea. Plus, the atmosphere is full of it. Right? There's plenty around, so you can use it as a standard. The problem with oxygen is it's a gas. And you need very special equipment and high precision and high accuracy to work with oxygen as a gas. Because it can change volume easily depending on pressure and temperature. So we had to settle on a different standard. What we needed was one of the elements that was easy to obtain in pure form, in isotopically pure form. And we look to nature, right? Every living system on this planet is carbon-based. So carbon is easy to get at. Plus, fossil fuels are carbon-based, right? Oil, natural gas, coal, they're all based on carbon. So we have a ready source of carbon anywhere you want to look. So that's where we stopped. We settled on carbon as our standard. And our standard carbon is carbon-12. The isotope of carbon that has 12 nucleons, that is 6 protons and 6 neutrons. That isotope is our standard. And what we say is that this standard, each atom of that carbon isotope has a mass of 12, exactly 12 atomic mass units, out to an infinite number of zeros. 12 atomic mass units. So that's our fixed point, and everything else is measured against it. Even other isotopes of carbon are measured against it. So carbon-13 will be some other atomic mass units, but it will not be exactly 13. Right? All the other isotopes of all the other elements will be fractionals. They might be really close, right? Maybe really close to 13. That might go out a long, long, long way before you get another number. But This is the only one that's guaranteed to be 12 atomic mass units per atom out to infinite numbers of decimal points. Okay, so then why on the periodic table does carbon have an atomic mass of 12.01? And it has several more decimal places, but that's good enough for now. Why then is it 12.01? Because naturally occurring carbon has a mix of isotopes. It has this one, plus it has this one, plus it has that one, and several more. This is the most common one. This is the largest number of isotopes in naturally occurring carbon. But there's a significant number, there are a significant number of carbon-13 atoms in that mix, which skews the value upwards ever so slightly. And that's why we get 12.01 for naturally occurring carbon rather than 12. Okay, it's a weighted average, and we're gonna talk about that in a minute. That value is a weighted average of all the naturally occurring carbon isotopes in the environment. So what that means is that somebody's got to determine what that ratio is. And there are people that dedicate their lives to it. They do nothing but determine isotopic ratios in nature. All right. So now that we know and we have determined that carbon, naturally occurring carbon, has 12.01 atomic mass units per atom on average, right? If you go out there and look for an atom of carbon that has 12.01 atomic mass units for that atom, you'll never find it. It does not exist. This is a weighted average of a large collection of carbon atoms. Right? But it's very useful because now we don't have to know what the isotopic ratio is. You know, how many carbon 12s and how many carbon 13s and how many carbon 14s are out there. We just take our naturally occurring sample. It's already been determined for us that this is the average mass for every atom. Okay. So if we know that we have 431 atoms, let's just, for argument's sake, 431 atoms, how many atomic mass units does that represent? Well, we have our conversion factor. Right? Atoms on the bottom, because this one's on the top, and atomic mass units on the top, so 12.01 per atom. And then multiply it out. Okay. And we get, for that many atoms, they should have a mass in these units of measure of 5,176 atomic mass units. How about aluminum? Right? Now that we've established that our reference point is the carbon 12 isotope, then we can ratio everything else to it, just like we did with the copper and zinc earlier. Once you know and you have a reference mass, then you can ratio all the other elements to it. And that's what's been done. Now we know that, and we look on the periodic table and find that aluminum has an average atomic mass of including all its isotopes, an average atomic mass of 26.98. Atomic mass units per atom of aluminum. Right? So if we say, for argument's sake, that we have 75 atoms of aluminum, we can use that as a conversion factor. Atoms cancel, and that gives us 2,024 aluminum atoms. All right. Now, up to this point, we've been talking about atoms as individual particles. And that's valid, but it's difficult to count that many atoms, because if you have a sample that you can hold in your hand, you've got billions and billions of atoms. They're that small. So we've come up with a different unit of measure that keeps the unit manageable, but still has a handle on how many atoms there are. And that's called the mole. The mole is simply a number. It's refined over the years. Right? There are methods that can determine how many atoms are in this mole. Right? We're not going to go into that here. It's a little bit too complex for this course. But suffice it to say that 1 mole is a number. And it's based upon our reference carbon. So what we're saying is that if we have 12.01 grams, right, before we had this many AMUs per atom on average. But the way the mole is defined, we can also say with that same number, this is grams per mole. And the abbreviation for mole, M-O-L-E, is MOL, right? Go figure. Why don't I just use the whole name? Instead, the abbreviation just drops E. So this same number on the periodic table, the atomic weight for each of the elements can be interpreted as either atomic mass units per atom or grams per mole of those atoms, right? So the mole must be a huge number, right? And in fact, it is. It's 1 mole is 6.022 times 10 to the 23rd things. In our case, the things are atoms, but you could still say anything else, ions, right? You could have that many ions and be a mole of ions, or you could have that many molecules, like molecules of water, and it would be that number of molecules of water. You could have a mole of chickens, and it would be that many chickens, right? It's a way of counting numbers of things. And it's given a special name, Avogadro's number. Avogadro was an Italian scientist back in the early 1800s. And the work that he did and the follow-on work that was done by one of his students, name was Cannizzaro, allowed us a way to count numbers of atoms and compare atoms of this element with that element. Okay, scientists call it elegant. If it's simple and explains a lot, we use the term elegant. His was an elegant explanation. But Avogadro didn't determine this number. It came later. But because of the work he did, he's given credit. His name is attached to it for posterity. So if we say 1 mole of carbon has this many atoms, and if you have that many atoms, that mole will weigh exactly 12.01 grams of naturally occurring carbon, right, with all of its mixture of isotopes. And because we have an equivalence here, right, 1 mole equals this many atoms, that's a possible conversion factor, either this way or that way. Or we have another conversion factor possibilities, this many atoms of carbon per 12.01 grams of carbon, and you can flip it, right? Again, because conversion factors are equal to 1. Or you can go from this side to that side and say 1 mole of carbon is 12.01 grams, or flip that way. So with this expression, we have 6 possible conversion factors, depending on your need. All right. So if you go to the periodic table and you look at each one of those little squares, you find 1 whole number for the number of protons, the atomic number, right? And that's unique for every element. Each element has a different number, atomic number. And they also have different atomic masses, but those atomic masses can be interpreted as grams per mole for the atoms of that element. So if you look periodic table, you say 1 mole of aluminum weighs 26.98 grams, or 1 mole of gold weighs 196.97 grams. Okay. These are just examples. Now, that is more useful. Atomic mass units, while true, are not very useful in the laboratory. Grams and moles are much more useful because we have devices in the laboratory that can actually measure mass, right, to very high accuracy. Right? I have one in the lab here at New River that will measure down to 4 decimal places of a gram, which is what? We go 1, 2, 3, that's 0.1 milligrams. Okay. And that's pretty good. Okay. It's not always what you need in a research laboratory, but for a student lab, that's really good. That accuracy is excellent. All right. So let's see if we've learned anything up to this point. So what's the question? You're given 63.55 grams of copper. How many copper atoms is that? Well, you need a conversion factor, don't you? Right? Conversion factor. And to go from mass to numbers, it's always mass to moles first. Then if you need numbers of atoms, actual numbers, then you use the equivalent conversion factor for moles and atoms, right? The 6.022. But at this point, we just need to get rid of grams and leave us with moles, right? That will tell us what number, a value for number. If we're actually going to do the numbers, then we'll go another step. Right? So, how much does 1 mole of copper weigh? What is its mass? Go to the periodic table. And we find that copper is 63, 50, 55. Okay. So the grams cancel, and 63.55 into 63.55 is 1. So 1 times 1 is 1 mole. So we actually have 1 mole of copper atoms. Now, if we need the exact number, 1 mole we know is equal to this. Right? So that's how many copper atoms you have if you have exactly 63.55 grams sample. Now, with one caveat. Early on in the semester, we made a big deal out of uncertainty. So this implies that you know that you have exactly that many number of copper atoms. But with the uncertainty of our measurements, it could be a little bit off from there. It could be 6.021 or 6.023. Right? But we're saying for argument's sake that we have that many atoms. Just recognize that there is always uncertainty in every measurement. All right. Here's another one. Which of the following is closest to the average mass of 1 copper atom? Right. This would be an easy question to answer on a test, because you know an atom's not going to weigh grams, that many grams and that many grams all the way down. It's got to weigh a really small value of grams. So test taking technique says the answer is E, and it is. But here's how we got there. Let me see. Do I need to do this one, or is it animated? It's animated. So I have it here. There we go. So what we have is 1 copper atom, right, is how many moles, right? Because the bridge between mass and numbers is in terms of mass by grams and moles. Right? So if you're bridging the gap between numbers and mass, sooner or later, you're going to need to know molar mass, the atomic mass. So that's what we've done here. First, we had to convert this atom into the number of moles of copper. Okay? So atoms cancel, divide this by that number, and that says we've got that many moles of copper. Right? It's a very small fraction. And then we take that number of moles and we convert it into grams with this conversion factor. Right? And those units cancel and leave us with grams of copper, just like we have wanted. So that's the thinking part of the answering the question. The rest is number crunching. So we crunch these numbers and we find that yes, 1 copper atom is 10 to the minus 22 grams. Very, very small. How about the number of iron atoms in 4.48 mole sample of iron? This should be a simple one-step process, because we have a relationship between moles and numbers that we can apply directly to that value. Okay. So here's what we start with, and here's our conversion factor. Atoms on top, moles on the bottom, so that we can cancel moles. Okay. When we cancel moles and multiply these out, we find that many moles of iron is that many numbers of atoms. Okay, so we have a sample of aluminum, 26.98 grams of aluminum, has the same number of atoms as how many grams of gold, AU? Well, this is where we start. And what I like to do with word problems is extract information from the problem, put it on the board or on paper in a form that's not cluttered with prose. One thing you'll realize, if you haven't already, is that word problems, while necessary, on tests, they're designed to confuse. In other words, they may throw stuff in there you don't need, or they may not give you everything you do need. You have to go find some of it. So I find that pulling things out of that problem and putting it in a form that I can understand and use is a way to get around the confusion. And also, they're designed to confuse so that the test taker will get the answer wrong unless he or she really knows the subject. Okay. All right, so we're starting off with 26.98 grams of aluminum. And we want to know how many atoms is that? And how many grams of gold would be the same number of atoms? So what we need to do is convert this into a value of numbers of something, right? So that will convert it to numbers. And then we want to know what's the mass of gold that will give you exactly that same number of moles. Right? So we need a value here for aluminum, which is 2698. Okay, we're making it easy on ourselves. This is equal to 1 mole. So 1 mole of aluminum and 1 mole of gold have the same number of atoms. And 1 mole of gold equals what? Well, go look it up on the periodic table. 196.97. That many grams. Rounded off, 197 grams. Okay. Now, the problem, the way it's set up, converts to 1 mole. Right? But we could do the same problem with a different value here. We could say 50 grams of aluminum would be how many moles? Well, it'd be more than 1 mole, of course, but it would be an exact value or a value. And then we'd say that number of moles is equal to the same number of moles of gold. And then we would take that and use a conversion factor for gold to find grams. And so it doesn't have to be exactly this number. It's just, that's our example. All right. So let's say we have magnesium and zinc and silver. Go. And we have 100 grams of each one. All right. Which one has the greatest number of atoms? Think of it in these terms. If they're exactly the same mass, can they have the same number of atoms each? The answer is no, because each atom of different elements has a different mass. So they will have a different mass. One of them will be the lightest, one of them will be the heaviest. Excuse me, one of them will be the most number of atoms, one will be the least number of atoms, and the other will be in between. So if we're just going to put them in order, all we need to know is what's their relative molar masses. Right? Magnesium is 24.31 grams per mole. Zinc is 6538 grams per mole. And silver is 107.87. All right. So think of it in these terms. How many atoms of each would it take to make 100 grams? All right. This one's already more than 100 grams per mole, so it would take less than a mole, wouldn't it? This one would take less than a mole, less than 1 mole to make 100 grams. Right? This one would be greater than a mole. And this one would be greater than a mole. Right? So this one has the least number of atoms of those. We need to know, how do those compare? Which one's larger in numbers? Well, how many atoms does it take to make 100 grams of this one? It takes a lot. Does it take more than or less than this one? It takes less. The greater the mass of the atom, the fewer the atoms required to make up that mass. So this one here will have the greatest number of atoms because each of the atoms weighs less. Means you need more of them to make up the same mass as the rest. All right. How about this one? Let's see. I'm going to leave this information right here because it's the same silver, zinc, and magnesium. All right. Let's see. Let's do that one. This is still magnesium. This is still zinc. This is still silver. But this is A. This is B. And this is C. So just flip it. All right. So if we're just comparing these, putting them in order of greatest number to least number of atoms. Then if we have 107.9 grams, and zinc we have 70 grams, and magnesium we have 21 grams. Okay, if we're just going to put them in order, why don't we look and see, are they equal to 1 mole, less than 1 mole, or greater than 1 mole? Like, that'd be a good place to start. Okay. How about this one? 21 grams is less than 1 mole. Less than 1 mole. 70 is greater than a mole. And 107.9, that is exactly 1 mole. Right? So silver is going to be in the middle. Greatest to least. Greatest number of atoms, which one's greater than a mole? Zinc. And magnesium is less than a mole. So that's the order: zinc, silver, magnesium. Actually did the calculations here, but we can reason it the same way. All right, that means B is zinc, A is silver, and C is magnesium. So we put them in order with different masses. Okay, this is just a reminder of how to solve problems. And this is good for any type of science problem. What the first one is where are you going? Another way of saying that is, what's the question? Right? Every problem has a question that needs to be answered. Right? Then you need to say, all right, with this question, where am I starting and how am I going to get there? Right? So that's why when I know the question, then I pull information from the problem and put it on the board or on a piece of paper in a form that organizes the information in a way that I can understand it. That's given. And then you look for what's missing. That's the answer to the question. And then you can devise a plan on how to get there with the information you have, or do I need to go find some other information? For instance, and very often from the periodic table, right? Or you may have useful information, and each one of these review documents in the back has a periodic table, and it has some useful information, right? Like that, formulas, maybe this list of polyatomic ions. And that useful information, by the way, will be included in a separate document for every exam. If it's on the back of the review document, those pages, they will be available for the exam. If you go into the module for the exam, before you take it, find that useful information document and print it, because it's okay to use that during the exam. Then when you take the exam, when you go into lockdown browser, it's going to lock you out of everything, right? You can't get to that information after you go into lockdown browser. So print it out first, then go into the exam, and you'll have it ready and available for when you look for information that you might need. And then once you've solved the problem, you think you've solved the problem, the last question you ask yourself is, does the answer make sense? Right? If the answer is, what's the mass of an atom of copper? Right? Or that was our example. And you get an answer, you've calculated an answer that comes out as 110 grams. You know, there's something wrong with that picture, because atoms don't weigh that much. So always question yourself at the end to see if the answer makes sense. One way to do that sometimes is estimation. Can you do an estimation of the calculation in your head? Right? If you can get within an order of magnitude, that is a power of 10, of the answer that you got on paper, then it's probably right. That just checks you against, did I put the numbers into my calculator correctly? One mistake that students make too often, and this is sad, is that if the calculation says A divided by B, when they put it in the calculator, they put it in the calculator so that B is divided by A. And of course, you're going to get the wrong answer if you don't know how to operate your calculator. All right. So I've used this term before, and just by way of definition, molar mass simply means the mass in grams of 1 mole of the substance. So we're expanding beyond atomic molar mass. Right? Molar mass of an element is the number of grams of 1 mole of that element. But it doesn't have to be just the element. You can have a molar mass for a compound too. If you combine several elements into a compound, you can also calculate the molar mass for that compound. So here, we just looked this one up on the table. 14.01 grams per mole is the molar mass for the element nitrogen. But suppose we have a compound like water, right? How do you get the molar mass of water? Well, there's the formula. We have if you have 1 mole of water molecules, 6.022 times 10 to the 23rd water molecules. If you have that many, you also have 2 moles of hydrogen and 1 mole of oxygen. So if you have 2 moles of hydrogen and each one of them is 1.01 grams per mole, you just say 2 times that. And of course, oxygen is 1 times whatever its molar mass, atomic molar mass is. So this is 2.02, and this is 116.00. Add them together, you get 18.02 grams per mole of water. That's how you calculate the molar mass of a compound. Any formula, you can do that. Even one as big as barium nitrate. So this is a good one to work with because there's potential for mistake here. And I'll show you where it is. If we have this formula for barium nitrate, first of all, is that correct? Right? We've done these before. Barium is where? Well, barium is an alkaline earth, so it has a 2+ charge. And nitrate is a polyatomic ion with a -1 charge. So 2 minuses balances the 2+. That's a correct formula. We need 2 of these polyatomics. That's why it's in parentheses, because you cannot split a polyatomic ion. If you need more than 1 of those negative charges, you have to use a subscript outside the parentheses. Okay. So now that we know that is correct, what is the molar mass? Well, if we have 1 mole of barium nitrate, how many moles of barium do you have? We have 1 mole of barium, right? And what's the molar mass of barium? Well, let's see, let's look it up. 137.33. 137.33 grams per mole. How about nitrate? How many nitrogens do we have? 2, right? That subscript says that there are 2 nitrogens. So that's 2 times 14.01. And we have how many oxygens? 2 times 3 is 6. We have 6 moles of oxygen. And this is all in 1 mole of that compound. So we have 6 times 16. So you multiply, add them all up. And you should get 261.35 grams per mole. Per mole of that compound. All right. Now, I think this slide is useful sometimes. If you're going to memorize things, it's useful. But if you stick to dimensional analysis and using conversion factors, then you can reason out which way to apply a conversion factor to get the answer. This says that moles of a compound is mass of the sample divided by the molar mass of the sample. That's true. It works. But if you say, what is molar mass? Right? Molar mass is equal to the mass in grams per mole. So once you have the ratio of grams to mole, that's your conversion factor for any operation that has that as the potential conversion factor. That just proves that the grams cancel. Notice that when you have in the denominator, you have grams per mole in the denominator. If you think back to your math classes, the denominator of the denominator is the numerator. So this one flips to the moles on top. That one is still in the denominator and cancels this numerator. So you're left with moles in the numerator. That's what we're saying here. That is this one flipped. All right. And it's another way to approach it. What's the molar mass of nickel 2 carbonate? All right. Now we're getting into the territory where preparation was essential. In previous chapters of this, previous parts of this course, you learned how to write compounds. If you didn't master that technique then you're going to be lost now, because you have to know how to write these compounds in order to determine their molar mass. You can't write the compound, you can't determine the molar mass from the name of the compound. You have to have the formula. So nickel 2 means nickel is a 2+ charge. And carbonate is a polyatomic ion. You can look it up. Carbonate is a 2- charge. So one of these balances one of those. That is the formula. Now if you do, you can calculate the molar mass for this. You just need 1 nickel, which is 5869. That's for nickel. Carbon is 12.01. We did that one earlier. And oxygen is 3 of them times 16. So add them together. Right? And you get 118.7 grams per mole because you knew how to write the compound. Okay. Let's see how we're doing on time. It's a little after 10. I think what we've got till 11. 11. Yes. Let me see how many more slides we've got so I'll know whether I need to hurry up. I think we're good. We're good. We can take our time. So if you have equal mole samples of each of these compounds, right, N2O or aluminum nitrate or potassium cyanide, what we want to know is rank these from least to most number of nitrogen atoms in each sample. Equal mole samples, right? So it doesn't say how many moles. So as long as they're equal, we can pick whatever we want. So let's just say we have 1 mole of each, right? 1 mole of each. Well, let's do it this way. We have 1 mole of compound. 1 mole of compound. 1 mole of compound. Right. And this is where I start using what I call my Henry Ford method. It's an assembly line, because we're going to do the same type of operation all the way across on each one of them. There are certain factors inside the operation that change depending on the compound and the elements, but the steps are the same. We want to convert that to what? Well, it says we have equal moles. Which one has the least number of nitrogen atoms? Least to most, least to most. So we need nitrogen atoms. So if we have compound. If we have 1 mole of compound, why did I put it down here? So it would cancel this, right? We don't want to keep that. What we want up here is moles of nitrogen. Moles of nitrogen. So it's going to be different for each one. This one has, for every 1 mole of compound, we have 2 moles of nitrogen. for every 1 mole of aluminum nitrate, we have what? 3 nitrogens. And for this one, we only have 1. Okay. So these cancel. That. And now we have 2, 3, 1 moles of nitrogen. All right, so if we rank them from least to most, potassium cyanide, nitrous oxide, dinitrogen monoxide, and aluminum nitrate is the last one. So it should be this one right here. Okay. All right, what are they throwing at it this time? If we have a 100-gram sample of each of the following, okay, we're having the same mass this time, not the same moles, the same mass. Then the question is, rank them greatest to least number of oxygen atoms. Okay, this would take a little bit more work, but if you're methodical about it, you know what the end result needs to be, then you can get there. This is also another Henry Ford problem. Okay. We have 4 compounds. We have water. We have nitrous oxide. We have C3H6O2, which I think is propionic acid. Okay, and we have carbon dioxide. All right. So we're given 100 grams of each one. All right, remember when you have mass and you want to go to numbers, you need molar mass. That relates numbers to mass. Molar mass always does that. So if we've got grams here, grams has to be on the bottom and moles on the top. And what is that moles of? That's moles of the compound. Compound moles. Right? Each one is going to be different. Right? We did water before, so I remember that. So that's for every mole of water compound, we have 18.02 grams. Nitrous oxide would be 2 nitrogens, right? 14.01 times 2, and then oxygen is 16. Okay. So that's 28.02 plus 16. 28.02 for the nitrogens and 16 for the oxygen. So that's 44.02. There we go. Now let's do this one. 3 carbons. 3 times 12.01, 6 times 1.01 for hydrogen, and then 2 times 16 for oxygen. Right? So that's 12.01 and multiply by 3. And then we'll add to that 6.06, right? 6 times 1.01. And then 32 for that, 2 times 16. So this was 74.09. And the last one, CO2. That's 1 carbon and 2 oxygens. Right, so 32 enter and 12.01 plus that. 44.01. There we go. Now, that cancels the mass and leaves us with moles of compound. Go back to the question. Number of oxygen atoms. If we're ranking them in numbers, then we can stop at moles. Once we know the moles of oxygen for each sample, we can stop there. We don't have to go all the way to Avogadro's number because we're only putting in the order. All right, so what we need is another conversion factor that takes out compound and leaves us with oxygen. And this is moles of each one. So how many oxygen atoms in one compound? Just one. Right? How many oxygen atoms in this one? Just one. One per compound. In this one, we have 2 oxygens per compound. And this one, we have 2 oxygens per compound. All right. So that gets rid of the moles of compound and leaves us with moles of oxygen. Okay, now that's the thinking part. The rest is number crunching. So if we take 100 and divide it by 18.02, right, it's in the denominator, and then times 1, we get 5.55. Moles of oxygen. How about the next one? 44.02 divided into that value right here times 1 is 2.89, 2.49. Okay, how about this one? 100 divided by 74.09, but also times 2 is 2.70. And this one divided by 44.01 times 2 is 4.54. There we go. This is moles of oxygen in each of these 100-gram samples for the different compounds. Right? So put them in order from greatest to least. Greatest is water. The next one, CO2. The next one, C3H6O2. And the last one, nitrous oxide. All right. All right. So when I made this slide up originally, I went all the way to the number of atoms. You don't have to do that. Right? We could stop with this calculation right here. But there they are, and they should give us the same order: water, carbon dioxide, propionic acid, and nitrous oxide. So when you have a problem like this, the best way to approach it is Henry Ford, because you know that each of the calculations is going to be a similar format. You just have to change individual numbers to get where you're going. And if you lay one out first so that you know that, all right, this is correct, units cancel, I get the answer I want, then you can set the rest of them up exactly the same and just change the values that are unique to this particular compound. Okay. So let's make room for the next one. How many grams of fluorine are contained in one molecule of boron trifluoride? One molecule of boron trifluoride. All right. You'll notice that boron and fluorine are both. Oh, we got another visitor. Okay. I like to mark down the ones that zoom in. Here we go. Fluorine and boron are both nonmetals. So we name them with the type 3 convention. So boron trifluoride tells us the formula is this. Okay. So if we have one molecule of boron trifluoride, we have one molecule of boron trifluoride, how many atoms of fluorine is that? One molecule of this implies 3 atoms of fluorine. Like just the ratio there. So if that's our starting point now, we have 3 atoms of fluorine. Then what we can do is convert that into moles of fluorine. Remember, if we're trying to find out mass, the ratio, the conversion factor is moles and grams. So we got to get moles here first. Okay. So how many atoms in a mole? 6.022 times 10 to the 23rd. And that's 1 mole of fluorine. Now that we have those canceled, we can go to moles here, grams there. That gives us our value, grams. So 1 mole is how many grams of fluorine? 19? Yeah, 19.0. Okay, so that's the thinking part. The rest is just number crunching. So if we take 3 times 19, divide by this number, we will get a very small number. Okay, there it is. 9.465 times 10 to the minus 23rd grams of fluorine in 1 molecule, just a single molecule with 1 boron atom and 3 fluorine atoms. That's the mass of fluorine that you have in that 1 molecule. Very, very small number. All right. So we're going to shift gears just a little bit and talk about, well, let me preface this slide by saying when a chemist goes into the lab to determine the composition of a compound, right? How much of each element is in the compound. What they usually report is percent by mass. So much percent of, so if we had, if the compound were, well, I don't know, let's say glucose. They would report so much carbon, right? So we'd have X grams of carbon, we'd have Y grams of hydrogen, and we'd have Z grams of oxygen. Right? We know that those are the only elements in glucose. And they would say that many grams, that many grams, that many grams. And this would be a total of X plus Y plus Z. So for each one of these, they would have a percentage composition of X divided by X plus Y plus Z times 100. We'll do that for each one of them. And for this one. And this would be percent mass mass. Okay. If I haven't said it before, I'll say it again. Percent is a tricky number. It's dimensionless. It just means parts per 100. And so it could be grams per 100 grams, or it could be grams per 100 milliliters, or it could be milliliters per 100 milliliters. Right? So it's important to say what it is. Mass mass means so many grams per 100 grams of sample. And that's what they would report, percentage for each one of these elements in the compound. Now that's when you're going from analysis to a report on the compound. But if you know the formula of the compound, you can calculate the theoretical mass of each of the elements in it. That's what we're going to do next. So that by definition is what I just showed you. the mass of the element in the compound plus the total mass of the compound times 100. If we know the formula, though, we can ratio the masses, the molar masses of the elements against the compound. So if we have this formula, iron 3 oxide, we know that's the formula. Well, how do we get at masses? Right? Because that doesn't say masses. We know how to find the molar mass, right? So what you do is you say, all right, I've got 1 mole of that compound. Right? What's the molar mass of that compound? Well, we have to look it up. 2 irons, 55, 85. 2 times 55.85 grams per mole. This is moles. And then we have 3 oxygens. Okay, so we add those together and we find out what's the molar mass of that compound. Right, this is 111.70 grams. And this is 48 grams. So we have 159.70 grams. That's our sample size. That would go down here, right here, mass of the compound, for 1 mole. So how many moles of iron do we have? Well, we have 2 moles of iron, right? 2 moles of iron for that total. So our ratio will be 111.70 grams per 159.70 grams times 100. Let's see. And 111.7. That would be 69.94% iron. Okay, we do the same thing for oxygen. 48, and we got the same denominator. So 48 enter and 159.7 divide. This one is 30.06% oxygen. Right? And this should add up to 100, shouldn't it? That's just 1. Yeah, that's 100%. Okay. So that's how you calculate the percent of each one of the elements in a compound if you know the formula. Okay, we just did iron for that example, but you can do the oxygen too. All right, what's next? Got a half hour. Let's see if I can finish up in a half hour. Morphine, derived from opium plants, has the potential for use and abuse. Here's a word problem. And what do we need to know from that first sentence? Maybe the name of the compound. That's it. The rest of it is fluff. Its formula is this value, C17H19NO3. What percent by mass is the carbon in this compound? Right? We do it exactly the same way as we did the iron 3 oxide. We find out the total mass of the compound, of 1 mole of a compound, and then what's the mass represented by each one of the elements? Well, we have 17 moles of carbon, right? So we're going to do that. So 17 times 12.01 would be in the numerator. And then the denominator, you would have to calculate the entire molar mass for the compound and put that in the denominator. And if we do that, like this, right? There's the carbon, here's the carbon 2. Right? When you do this calculation, you got to put the the element that you're looking for also has to be in the denominator, right? So each one of these elements, 1, 2, 3, 4 elements in the bottom, 1 element in the top, and that's 71.6% carbon for morphine. All right. So here we are with a 100-gram sample of each one of these same compounds we looked at earlier. Highest to lowest percent oxygen by mass. So in this case, you would run through each one, calculate the percent oxygen, right? Before, what did we do? We said the number of moles of oxygen, right? We compared those. Now we're comparing the percent of oxygen in each one. So we used the previous 2 slides, what we did there, and run through that entire process. And this is a shortened version. This is the percent oxygen in each one. That's for water, right? There's water. I mean, there's oxygen, and there's your hydrogen. So you do that same calculation for each one, and then you compare them. And it turns out that by percent mass composition, water is the greatest. Carbon dioxide is the next. Actually, that's the same order as before, isn't it? Could be coincidence. It's not always that way, but in this case it is. The same order as before. All right, so why we spend so much time on percent composition? The reason is, if you know the percent composition, if an analytical chemist did the analysis for you and gave you these values, percent, whatever, carbon, percent oxygen, percent hydrogen, then you can use that information to start to get a handle on what is the formula for that compound. And our starting point is to use that information to determine the empirical formula. So we need to define what is the empirical formula. The empirical formula is the simplest whole number ratio of moles of each compound, of each element in the compound, excuse me. Simplest whole number ratio. We can find it from the percent composition. For example, if this is your empirical formula for a compound, CH, the ratio of moles to moles is for every 1 mole of carbon, you have 1 mole of hydrogen. Right? Now that could be this compound, or it could be this compound. Could be any number of compounds, right? The simplest whole number ratio for this one is 1 to 1, and this one is 1 to 1. So this empirical formula is the same for both of them. Right? And you're probably wondering, what good is that, right? We know the empirical formula, but it didn't tell us which compound it is. All right, that's coming. We're going to get there. But with the percent composition, you can get at the empirical formula. Then you need to go one more step to find out which one it is. All right, so we're going to do that first. Well, actually, I'm going to explain. If we take this formula and we put the simplest multiplier on the outside of the parentheses, it's 2. And for this one, excuse me, not nitrogen, hydrogen. That one is 6, right? So we have the empirical formula inside, and we have this multiplier, an integer, out here. We need to find out what is that value, okay? And that will give us the molecular formula. If we know what this multiplier is, and we know what the empirical formula is, we can say, all right, if it's 2, then it's that compound. If it's 6, it's this compound. There's your example. All right. So first we're going to determine the empirical formula for a compound. And then I'll show you what the next step is for finding that value right there. So here's our example. We have a gaseous compound, which is neither here nor there for this operation, but we do know that it's made of carbon and hydrogen only. Only carbon and hydrogen. Okay? And it was analyzed to find that it has 83.65%. 83.65% carbon. Right? If there's only carbon and hydrogen, how much hydrogen is there? It's what's left over, right? 100 minus that is this. So that's 5, that's 3, and that's 6, and that's 1. Right, should that be right? 10, 10, 10, 9, 10. That's right. So now we know percentage composition for both of them. But what does the formula mean? What does that mean? That doesn't mean mass to mass. That means numbers to numbers or moles to moles. It doesn't mean mass. Right? So we have to get at the number of moles. What does this represent in terms of moles of each element in the compound? Right? We can't do it from this. Why? Because percent is a dimensionless number. We can't change percent into anything. So we have to make an assumption. What if you have 100 grams of this sample? If that's your sample size, now we know 83.65 grams per 100 gram sample. So now we know it's this grams. And remember Proust's law of definite composition. Every compound has a ratio of mass to mass of the elements. And it's constant, doesn't change, it's definite. So if it's this percentage, that percentage, then we know that this ratio and this ratio are fixed for that size sample. Now that we have grams, we can go to moles. So how do you get to moles from grams? Well, you need molar mass. So carbon is 12.01 and hydrogen is 1.01. All right, and this ratio is fixed. Mass to mass, whatever moles to moles we find is the same, is a definite ratio. It's fixed. So if we have 83.65 grams and divided by 12.01, we have 6.97. 6.97 moles of carbon. And for this one, 16.35 divided by 1.01 is 16.19 moles of hydrogen. Okay, we're not there yet. This is the correct ratio of moles, 6.97 to 16.19, but you can't use that in a formula. You need whole numbers. So we got to find a way to get the whole numbers. Mathematically speaking, once this ratio is fixed, we can multiply or divide both of them by the same number, and the ratio is still fixed. So I take the smallest one and divide by its value. Right? That's equal to 1, obviously. 16.19 divided by 6.97 is 6.97. And that's 2.3. Okay, we're getting there. With this ratio, how do we get rid of that fraction? Well, we can multiply, can't we? If we multiply by 3. Yeah, multiply by 3. Right. If this is actually this is 3, 2. That's about a third. Now, at this point, we're starting to take into account experimental error. Right. This is very close to a third. 0.33 would be a third. So how do you get rid of a third in this ratio? You multiply both of them by 3. So 3 times a third is 1, isn't it? So if we multiply by 3, now the carbon ratio is 3, and the hydrogen is 3 times 2.63, which is 6 plus 1 is 7. So the ratio is 3 to 7. 3H7. This is the empirical formula. All right. Now we know it can't be reduced anymore because those are both prime numbers. You can't divide something into both of them. So that's it. That's the empirical formula. All right. So there we go. That's the first part. I didn't realize I had an animation on this one, so that's okay. It won't hurt to see it done twice. There's 6.965, 16.22, close. Divide the smallest one through everything, and then we get, multiply them by 3, and we get the empirical formula C3H7. Now, this is the empirical formula. What's the molecular formula? Well, the molecular formula is going to be the empirical formula times some multiplier. Okay? So this has what I call an empirical weight. Right? It has so many grams per mole of that formula. And we can calculate that as 3 times 12.01. Oops, 12.01. And then 7 times 1.01 and add them together. So this one has an empirical weight of 43.1 grams per mole of the empirical formula. Okay. What would this one have? If we multiply it by a whole number, then the formula weight or the molar mass of the true compound would be this value times that one, right? So whatever this one is, it was going to be a multiple of that one. So we need some way to find out what is the true molar mass of that compound. If we have the true molar mass, we can divide this one by that one and find out what that multiplier is. All right, so that's where we're headed next. So let's see, we still got those values. Yes. So by some other independent means, right? I can't go into that right now. We don't have time. But there are ways to get at the molar mass of compounds without knowing what the compound is. And we determined that the molar mass of the compound is 86.2. All right. What's the ratio? Well, it's fairly obvious. If we divide this one by 43.1, that's about 2. So that's equal to 2. And our formula is 2 times 3 is 6. And 2 times 7 is 14. That is the molecular formula for our compound. So you have to go through the empirical formula first. Then with an independently determined molar mass for the compound, you can calculate that multiplier. and apply it to the formula and determine its molecular formula. All right. Let's see. I only got 15 minutes left. Let me see what's left. I don't want to leave anything undone. Once I get over here. Okay. This is the last problem. So we can do this one too. I won't have to stop and explain things as thoroughly this time because you've already seen it done. So we extract the information from this problem. Now, in this case, we have carbon, hydrogen, and oxygen for adipic acid. What's adipic acid? It's a fatty acid, right? All true fats have fatty acids built into them, and that's one that's in our bodies. So what's the empirical formula for this one? 49.3% carbon. Carbon, hydrogen, oxygen. 49.3%. 6.9% hydrogen. And this is by mass, of course. 43.8%. All right. So, same as before. Assume you have 100 grams, and then the percents become mass. So now, with 100 grams, this is the ratio of masses. And Henry Ford says we convert grams, cancels, leaves us with moles. Moles. We just need oxygen is 16 grams per mole. Hydrogen is 1.01 grams per mole. Carbon is 12.01 grams per mole. So this gives us, this is the mass ratio. This will give us the mole ratio. Okay. We got a storm moving through, so if I lose connection, that's why. 49.3 and 12.01. This is 4.10. 6.9 grams divided by 1.01 is 6.83. And this is all moles. And 43.8 divided by 16 is 2.74. Okay. Next step, divide everything through by the smallest one. The ratio is fixed already. So we're just modifying the ratio with a common divisor. So let's see, this one's going to be 1, of course. And then this one's going to be about 2.5. Right? Now we're estimating to get really close to whole numbers. And then, let's see, 2.74. And this one is about 1.5. Okay. So now, how do you get rid of a half? Multiply by 2. Right? 1/2 times 2 equals 1. Right? So if we multiply these, each one by 2, we get 2 here, we get 5 there, and we get 3 there. So the empirical formula is C3, oops, fix that, C3, H5O2. Okay. That's your empirical formula for adipic acid. And there it is, 352, empirical formula. Now, what if we know that the molar mass of adipic acid is actually 146 grams per mole? So this is the molar mass. I'm going to abbreviate it molecular weight because MM just didn't look right. So this is 146 point, that's it, grams per mole. What's the empirical weight? Well, 3 times carbon, 5 times hydrogen, and 2 times oxygen. So carbon is 12.01 times 3. And hydrogen is 5.05 because it's 5 times 1.01. And then oxygen is 32 because it's 2 times 16. So this one is, the empirical weight is 73.35. So if we divide this into that, what are we going to get? Divided by 73. That's about 2, isn't it? 2 times that? Yeah, that's about 2. So the multiplier here is 2. And the formula is C6H10O4. Okay, that's how it's done. Oh, that's it for chapter 8.